Hey everyone, welcome to the video today. Today we're going to be looking at Newton's method, which is, well, let me explain what it is now. Um, in maths, we're not always able to solve things, right? So that may come as a surprise to you, but if we've got like, say, y equals f of x, and we're trying to find the zeros, so that the y and the, the x-intercepts there, we're trying to find those zeros. We so far we've been doing it with, well, you could use quadratic equation if it's a quadratic, but you could use factorization, and there's a number of different ways you can do it. But that's all assuming that you can factorize and you can, it is a quadratic, so there's only sort of limited ways. And in like a lot of what we've studied so far, we give you things that can be factorized and that can be figured out, but that's not always true. You can't always factorize everything. There's definitely things that can't be. Um, and so, in the sort of the modern era of mathematics, I guess you call it, even though this is Newton, which is very old, but it's still relatively new, that we've come up with iterations and so approximations to things, and that's what Newton's method does. It gives us an approximation of in this case, we're looking for x-intercepts. We're trying to solve where a function is equal to 0. So we're solving here. So what we're doing is we're looking for to solve f of x equals 0, where the function is equal to 0, otherwise known as the zeros or the x-intercepts, however you like to call it. And this is going to be an approximation to those, and so that's what we're trying to find for this. So looking at this graph here, I'll show you what the iterations do. What I mean by iterations is that we just do it over and over and over again. And in most cases, I say most cases, then what Newton's method will do is every time we iterate it, every time we do the process over, we'll get closer and closer and closer to the x-intercept that we're trying to look for. And that's the basic thing of it. And I'll show you the formula in a second, but I'll show you how it works. So if we pick, so let's say we're trying to find this x-intercept, right? We've got 3 x-intercepts here. And what Newton's method says is that, well, firstly, you need to start somewhere near it. Okay, and I'll show you why in a second, right? So if we pick some point that we know is near it, let's say we pick this point up here, right? And it's going to be hard to sort of follow. And let's call this point there, the x value of that point, x0. We're going to say, well, we reckon it's somewhere near there. So it's somewhere approximately equal to that. So we're going to start at x0. And the what Newton method says, well, we're going to draw a tangent. And I'm going to draw it. And, sorry, really wobbly. So, I'm going to draw a tangent to that point. Oh, that's awful. I probably should just give up now. Let's just assume that that's the tangent. I've done it bad. If we draw a tangent to that point, and then we look at what the x-intercept of the tangent is, in other words, this point here, then we call that point x1, right? That's our next point. And what Newton's method says that that point will be closer to the x-intercept than x0 was, right? So this point here, that one, is closer to the x-intercept than that one. Okay, so we're sort of gotten a bit closer. And so that's good. And so then what Newton's method says, well, next, and this is a bit inaccurate. Let me try. We'll try to draw it again, all right? Because it's a bit steeper than that, and it's not going to be helpful to you. Sort of show. And so that x-intercept there, and so that point there, that there is x1. That's probably a little bit more accurate to sort of show you what's going on. So there's x1, and then we run it again. So at that x1, at that point, we draw a tangent line, and so let's just draw a tangent line again. Oh, I'll change colour, sorry. I'll just to make it a bit more helpful, but I don't really have that. I'll do it in black. So I'll do a tangent line there. So we do the tangent at that point. At that point x1, we draw the tangent at that exact point to the function, and then we look at where that line crosses the x-axis again, and that's our next point, so that's x2. And we keep doing that over and over and over again, because that gives us the point x2 on the blue line there. And if we draw the tangent to that, see how it's sort of cutting, it's getting closer and closer and closer every time I draw a tangent and do the x point, so that point will be x3 there. You can sort of see how it's zooming in. It's targeting in on the x-intercept. It's getting closer and closer and closer. So I hope that sort of makes sense. And so this usually works, and 90% of the time it works. Let me just show you a couple of examples where it doesn't. If I was doing, so again, I'm trying to find that x-intercept, but let's say I choose a point that's a little bit further away. Let's say if I choose this point here. Right, if I choose that point there, to still trying to find this x-intercept, but if I choose that point there, then the tangent line will go like this, and it will shoot back. Oh, let's see, now I can draw a tangent. I don't know why. Anyway, but then, so that will be your x1. So if that was x0 there, your x1 will be there. And so then I've got this point down here on the curve. I draw a tangent to that, and it comes here. So that's my x2 there. That's x2 down there, x2, and then I draw a tangent line there, x3. Can you see what's happened? Is that it's starting to zoom in on this, on that x-intercept, not this x-intercept. And so what it means is that it's just important that you get that you're closer to the x-intercept. You need to be sort of reasonably close to the x-intercept. The important thing is that there's a turning point here, right? There's a turning point there, and if you're on the wrong side of the turning point, it's going to go the wrong way. So you need to be within a stationary point. I hope that makes sense. Like if you're trying to find an x-intercept, you need to be on the right side of a stationary point. And the same will happen if I picked a point. See, there's a stationary point there. If I picked a point over there, it's gonna get there, and then there. It's gonna zoom in on that that x-intercept, not this one here. So I hope that makes sense. That's the process. And so, we can prove it, but I'll save that for your maths teacher in class. Won't do it here. But what it means is that what we end up with is this particular formula. So if we're trying to find x-intercepts, in other words, we're trying to solve where the function is equal to 0, then if we follow this iterative process where xn plus 1 is equal to the previous value of x, so xn, take away the function of xn divided by the derivative f dashed of xn. And we just keep doing that over and over again until we're satisfied with how accurate it is. And that's actually what your CAS calculators do when they're giving you an x-intercept. They're just applying this method to get closer and closer, and they keep doing it until the decimal places stop changing, and then they consider that to be accurate enough. I hope that makes sense, but let's have a look at an example and it will sort of make a little bit more sense. So here we go. So looking at this, so starting with x0 equals 0. So we're going to guess that the x-intercept is 0. It's not. That's close to there. We want to find x3. In other words, we're going to iterate 3 times. We're going to find x1 and then x2 and then x3. So we're going to do this job 3 times for this particular equation. So we've got an equation cos 3x is equal to sine x. Now remember, when we're trying to use Newton's method, we need a function that's equal to 0. We want to try to solve f of x equals 0. So what we actually need here, we just need to rearrange this a little bit. Let's call f of x, we'll make that cos 3x, take away sine x, okay? Because that'll be my function. If I solve that that's equal to 0, then that will give us the same solutions as this equation here, which is what we want. So our f of x is cos 3x take away sine x. We're going to start with the point x0 is equal to 0, and we're going to iterate, okay? Now, I'm going to do this all on calculator, and you'll only ever be expected to do this on calculator. And so I'll just sort of write down the first few steps so you can see, and I'll leave that there so you can see it. And then I'm just going to switch over to the calculator, and hopefully you'll follow what I'm doing on the calculator versus what I'm doing here. So x0 is equal to 0, so therefore x1 is equal to, so here n's equal to 0, so there, so x1, the previous one, x1 is equal to x0, take away f of x0 over f dashed of x0, okay? So what is x0? x0 is 0, so it's 0, take away f of 0 over f dashed of 0. Okay, so I've got the function, I plug in for this one here, I plug in 0 into the function, I need to find the derivative, and then I plug in 0 into the derivative, and I evaluate that, and that will give me x1. And then to find x2, I do the same thing over and over again to find x2 and then to find x3. Okay, so let's flick over now to CAS calculator to do this. Okay, so I'm going to define my function firstly. So I'm going to say f of x. I'm going to define it as, and I've already forgotten my function, it was cos 3x take away sine x. Okay, so there's that. I'm also going to define the derivative, and I'm just going to call the derivative gx. Okay, so that's just the derivative. It'll just make this process quicker. So I'm going to do the derivative, d dx of f of x. Done. I'll just check that it's done that correctly. I'll just do g of x. Yep, that's the derivative of f of x. All good. So what I want to do now is I'm going to do my first iteration. So x0 was 0. So my x1 is going to be equal to 0. Take away fraction. And on the top line, it'll be f of 0. Bottom line, it's going to be g of 0. And so I'm just putting all those things in. Top line is the derivative. Top line is the function. Bottom line is the derivative. So I'll put it into there, my iteration, and that's equal to 1. I'll just come back to my screen. And so that's equal to, I'm still on highlighter. That's equal to 1. So x1 is equal to 1. We'll go again. x2, I'm going to stop doing this in a second, but just to show you where it's coming from. x2 is equal to x1 take away f of x1 over f dashed. I know I'm on the bottom of the screen there, of x1. Okay, so what that's going to be equal to, it's going to be equal to 1, because x1 is 1, take away f of 1 over f dashed of 1. Okay, now I'm going to keep doing the rest on calculator here. So I need to find x3. I'm going to entirely do it on calculator now. So it's going to be 1. That was my previous value. Take away fraction f of 1 over g of 1. Remember, that's my derivative. That's equal to that mess. I don't care what that's equal to. I'm using calculator. I just want control equals. And I've got this value, so negative 0.9005. Okay, so that's x2. I'm pretty sure x1, x0 was 0, x1 was 1. That's x2. I need to find x3, so I need to do that process one more time. It's pretty gross now. I want to keep my accuracy as much as possible, so I'm going to use that full thing. I've just gone up and copied that down. So it's that. Take away fraction f. And I'm going to put that number in there again. I'll pop that into there, down here, and then G. It doesn't do bottom lines of fraction. If I went up to there now, it's not going to do it. And so I'll go Control C to copy that number. And I'm going to go back down to there and Control V, because it just doesn't like doing the enter thing on calculator. So I'll put all those points in there, and this will give you my x3. And so my x3, I'm just going to remember this because I don't think the question asked me for accuracy, negative 0.716. So negative 0.716, just going back to my document. And so coming back to here, 3, it was equal, I forgot what it is, negative 0.716, something. You get the idea. You can do whatever accuracy you would like. But that x3 was equal to x2 minus f of x2 over f dashed of x2. And so that's what we ended up with, blah, 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 blah. And so it's equal to negative 0.16. And if we actually go and sketch that, let's just quickly have a look at it. Going back to my CAS calculator, let's have a look at f of x. Let's set a graphs page, and we'll actually graph f of x. And so we've got that there. Which one we're looking at? We started at x equals 0. So let's just zoom in on this area here. Zoom in on sort of that area there. And at x equals 0, it's see how it's sort of it's up here, x equals 0. It's going to be zooming in on this particular x-intercept there. And so, or actually did it? What did we get? Let's just have a quick look at the answer. It's done the negative one, so let's just have a look at that again out of interest. That's interesting. Oh yeah, because the tangent will go that way, and the tangent. Interesting. It's zoomed in on this one here. That's interesting. We'll have a look at that in a second. So if we analyze the 0 there and we go between there and there, then we get negative 0.785. What did we get for ours? Negative 0.716, and I bet you if we iterated that again, that'll get closer and closer to negative 0.785, because that's how the CAS calculator did it. So it's interesting that our particular example here has actually zoomed in on not the intercept we wanted, because so the tangent would go down to here first, then it would come down to here, then it's I'll just sort of show you why. The tangent line will sort of go this way, right? and then it'll come down this way, and then it'll be like a zoom because it's so steep. The intercept's going to like shoot up really, really high. It's going to go far, and then it will get closer to this x-intercept. So it doesn't always work, and it doesn't always hit the x-intercept you want. So that's why it's really important to get fairly close to the x-intercept that you're after. Otherwise, it can give some undesirable results. But hopefully that makes sense about the method, about how we use it, and how calculators sort of use this as an algorithm to solve equations that we can't do analytically. Hope that makes sense. I'll see you in the next video.